Okay, lots of people had difficulty answering question 10, part 3. And from looking at the answers that you wrote, I realised there is still a lot of confusion around drawing and naming the hydrocarbons. So I said I'd make this little video to try and clear it up. Obviously, so far we have looked at a few homologous series, and they are alkanes, alkenes, and alkynes. Alkanes are fully saturated, all single bonds. Alkenes have double bonds, alkynes have triple bonds. Here I have the list of the prefixes that dictate the number of carbons in the molecule. And then over here I have two other parts. We either have methyl groups like so, or ethyl groups. If I was to draw that methyl group out in full, it's a carbon bonded to 3 hydrogens. That would look like this. If you were to draw an ethyl group, it's 2 carbons and 5 hydrogens that look like this. So remember the naming of them: methyl, which is essentially met, but YL at the end of it, group, and then ethyl, met, eth, and YL at the end of it for 2 hydrocarbons. Some people have a lot of difficulty in identifying the longest continuous carbon chain, so I'm just going to draw some examples. First of all, if you have a carbon by itself, it obviously has the prefix of met. If you look at carbon on the periodic table, it's located here. You'll see it's in group 4, so you have 1, 2, 3, 4 electrons on the outer shell. Alright. So if I was to draw those 4 electrons, they might look something like this. That means that carbon has 4 electrons on its outer shell. It needs 4 more to get a full octet, which means it has a valency of 4. If all of those 4 carbons underwent bonding, you might have a molecule that would look like this, and we say that is fully saturated. Why? Because all 4 electrons on the outer ring are all involved in a single bond. So if it's all single bonded, we say that is saturated. We know from looking at this that this is a methane molecule. Meth indicating 1 carbon, ANE indicating it's part of the alkanes, which simply are all single bonds. So that would be methane, the most simple form of one. You could also write CH4 being the molecular formula to indicate that that is methane. If I was to draw out another example, so what we're used to drawing are showing out all the single bonds with single lines like this. It's very clear on this molecule I'm after drawing where is the longest continuous carbon chain, and we like to number them. Because it's all single bonds, it doesn't matter if I name the carbons from left to right or from right to left. So I'm just going to go ahead, number them, and number them from left to right. I have 1, 2, 3 carbons, so straight away met, eth, prop. So this is prop, and again all single bonds, propane, like so. If I was to draw a hydrocarbon that's longer, so for example, I'm going to now draw 5 carbons in length, and on carbon number 2, I'll do all single bonds first, okay? So all single bonds, fully saturated with hydrogens, would look like that. Again, doesn't matter if you start naming the molecule from left to right or right to left. So I'm going to go ahead and number them from left to right. You see I have 5 carbons there: met, eth, prop, but, pent, and it still falls under the alkane family, so it ends in ANE. However, I could draw this molecule with a methyl group, so it means it is branched. Start off with 5 hydrocarbons again. I could have a methyl group, which I've drawn in a condensed format here, CH3, like this, instead of in the full format like that. And I could have another methyl group down here on this carbon. Again, I'm going to fully saturate everything else to look like this. Draw in all your hydrogens. Each carbon can only be involved in 4 single bonds, so make sure that there's no more than 4 bonds on any of the carbons. Now I have to decide, am I going to start naming the molecule from left to right or right to left? I usually say, well, you're going to identify which side of the molecule has more activity going on. Doesn't matter what side here, because if I name from left to right on carbon number 2, I have a methyl group. If I name from right to left, 1, 2, 3, 4, 5, on carbon number 2, again I have a methyl group. So this is essentially the same molecule from both directions. So I'm just going to name it from left to right again, 1, 2, 3, 4, 5. I now have 2 separate methyl groups. One of them is on carbon number 2 and one of them is on carbon number 4. So always starting with the smaller number, I indicate that by number which carbon has the methyl group. So on carbon number 2 and on carbon number 4, I have not one but two methyl groups. So I say dimethyl, so mono, di, tri. Usually for the one methyl group, we don't need to say anything, so you just say the number and then methyl. For two methyl groups, we say di. For three methyl groups, we say tri. 1, 2, 3, 4, 5 carbons in the backbone. Go down, meth, eth, prop, but, pent. So we're back again to pentane, like so. Let's get another sheet. Now, I could also look at this molecule and say, this is my carbon number 1. So you have to always look for the longest continuous carbon chain. If somebody was to argue with you that this is carbon number 1, then you have carbon number 1, 2, 3, 4, and 5. So going in this order here, which is not a straight line, it's a 90-degree angle, I still have the longest continuous carbon chain. So if I draw that molecule out exactly like I have done there, it would look like this. Okay? If I decided this is carbon number 1, this is 2, this is 3, this is 4, and this one is 5, then that means that this here and this one here are now my methyl groups. Why? Because any CH3 like this can be a methyl group, whether you draw it in a condensed form or in a full form like that. So if I now went to actually name this molecule, which is the exact same one we've already identified, I can say, well, I'm going to name it from left to right or right to left. I have my methyl groups on the same carbon each time. So I see here the smallest number first is 2. On carbon number 2, I have a methyl group. Attached to carbon number 4, I have a methyl group. Because I have two of them, we call it dimethyl. And then the longest continuous chain is meth, eth, prop, but, pent. So pentane. And again, I have the exact same molecule. So it doesn't matter if the carbons are in a straight line like this or if they're in branches, you always look for the longest continuous carbon chain. Some people gave me up homework that had things like this. So you had meth, eth, prop, then you had a C2H5 over here and a CH3 over there. Single bond, single bond, single bond, single bond. Okay, so looking at this molecule here, I could say I have carbon number 1, 2, 3 because that's our format of usually drawing them out in a straight line. However, if I'm looking for the longest continuous carbon chain, I have 1, 2, 3, 4 going this direction, or I have 1, 2, 3, 4, and 5 going this direction. So my longest continuous carbon chain is actually there. If I was to draw this out, the exact same molecule but draw it out in full, you might see it in a new light. So I'm going to do that. Okay, this is the same molecule as this one. When you see here C2H5, just like on the previous sheet, C2H5 can be drawn in short like this, but this is actually what it's representing. So instead of writing C2H5, I've actually drawn it out in full here. Now it's much clearer to see the longest continuous carbon chain, even though it's not at a lovely straight line like the way we like it. Carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. All of a sudden now,